just because I see a few familiar faces, but maybe some of you haven't met me before. Just to tell you a little bit about myself. So yeah, I'm currently a physicist at PPPL. I'm really interested in stability and transport in fusion plasmas, not just magnetic confinement, but more generally. I'm also more recently very interested in spin polarized fusion and questions about tritium fuel cycle. Okay, so this is what we're going to talk about today. First, I'm going to talk a bit about why we are doing fusion. So humanity consumes a lot of energy. It's like 2 times 10 to the 13 watts. It's a lot of power, right? And that's growing very, very quickly. An interesting thing that I kind of didn't really realize until now was just how unequal like the energy use per capita is. So this plot basically shows you the energy use per capita in any one of these countries. And then the x-axis is cumulatively what percentage of the global population that that country belongs to. And I think the point is that like these countries that are extremely populous but have very low energy consumption per capita, their populations are growing very quickly, and so is their energy consumption. And it would be really, really good if we had a clean, abundant, affordable source of energy that we could give them to help them develop their economies. Okay, there's also another object in the solar system that consumes a lot of energy or produces a lot, and that's the sun. If you take humanity's power consumption and literally square it, you'll get the power of the sun, which is like 10 to the 26 watts. It's kind of like a crazy number. What's really interesting is if you calculate the mass defect per second, so you just divide that power by the speed of light squared, you get how much mass the sun is converting into energy every second. So it's like 4 billion kilograms a second the sun is losing. And then humanity, by comparison, we're puny. We're like 0.2 grams per second. That's like our rate of mass defect as a civilization. So it doesn't sound like much, but it's quite a lot of energy. Okay, if you were to use deuterium tritium fuel, I'll tell you a little bit more about that in a second, you would need about 30 grams of DT fuel per second to power all of humanity's current consumption. It's like, it doesn't seem too much, right? 30 grams a second. It's like 10 to the 24 reactions per second. There's lots and lots of stuff that you use for deuterium tritium fusion, which is deuterium and lithium on Earth. So we don't really need to worry about supply shortages. If we were to use chemical reactions instead, we would need tens of millions of times as much fuel per second, which is many, many, many more reactions. So I kind of like the nuclear perspective, to be honest. It's just a lot more efficient in terms of how much fuel we use. Although every fuel obviously has its place. What is the DT reaction? Well, just very generally, deuterium and tritium, you fuse them together and you get helium-4 and a neutron. I'll talk a little bit more about this later. This is the world's first planned fusion power plant called ARC, which stands for affordable, robust, and compact. And here in the fusion core, you have deuterium and tritium, comes out as helium-4 and a neutron. And then in the blanket, what you basically do is you capture neutrons with lithium, mainly lithium-6, and you convert that into another helium-4 and tritium. So as you can see, even though we talk about DT fuel as kind of like the primary fuel we're going to be using, it's really, if you look at the full cycle, deuterium plus lithium gives you helium and some energy. Tritium is just kind of like the catalyst. Yeah.
I've heard of ARC. Is this just a general scheme or is this a specific company?
So ARC is the proposed power plant by a company called Commonwealth Fusion Systems, which is pursuing the high field approach to fusion. Yeah. And they're building something called Spark that's going to come online soon. Yeah. Smallest possible ARC, I think is what it really stands for. Yeah. Okay. There are loads of fusion concepts. I just showed you one so far, which was ARC. In the tokamak world, there are quite a few stellarators, mirrors, dipoles, laser inertial, magneto inertial. There are many, many, many more. I'm just going to be focusing on this today, but if you want to chat about the others, I'd also be very happy to talk about them. Okay, so what is fusion? Well, basically, it's a conversion of nuclear binding energy to kinetic energy. And And this plot here is one of my favorite plots in physics of all time, which is basically showing the average binding energy per nucleon versus the number of nucleons in the nucleus. So average binding energy per nucleon is just like how much work do we have to do in order to fully separate that nucleus into its constituent parts. And the point is that iron here, Fe56, that's the most stable thing in the universe. And then basically the goal is to go from the very light stuff, like, combine some stuff here and go, or fission is typically break apart something here and that way and release energy. Okay. I think there are, even for fusion physicists, I think there are two things that we don't always appreciate, which is one of the reasons fusion can release so much energy is that you basically have such a steep gradient here of the binding energy per nucleon versus number of nucleons. It basically means when you combine stuff, you really make those nuclei much more tightly bound. And you can see that helium-4 is quite a special thing, and that it's locally has a much higher binding energy per nucleon than any other nucleon around it. And that's why for fusion reactions, if you've got light stuff, you generally want to make it into helium-4 so that you can release as much energy as possible. And deuterium-tritium is, I'll try not to press the button so hard. Deuterium-tritium is not the most mass-dense fusion reaction. I think it might be helium-3 and deuterium, but it's pretty close. Okay, so anyway, deuterium-tritium, it goes through an intermediate state called helium-5. It's a so-called resonant fusion reaction, and you release a ton of energy by doing that. Okay, the mass defect divided by the mass of the reactants is about 0.7%. So that's how much energy we're releasing per reaction. For context, in chemical reactions, it's going to be like 10 to the minus 10 or something. So these are really releasing a lot of energy. Okay, how do we do fusion? Well, there's a very big problem when you try to do fusion, which is you find whenever you bring together any two nuclei, they're going to scatter a lot more times than they are going to undergo fusion, which is really what this plot is trying to show you. And so fusion is very slow compared with scattering from collisions. And this is a bit of a pain in the neck. And this fact about our universe basically dictates the kind of approaches that we take to fusion. And so basically, going back to that plot actually quickly, we can't just have beam-beam fusion typically, because most of the particles are going to scatter. You could do it, but it would be very hard to make it energetically worthwhile. And so what we want to do instead is, once these particles scatter, they still remain confined in our scheme, and they have many more chances to undergo fusion. Okay, so there's magnetic confinement on the left, where you use strong magnetic fields. The middle here is inertial confinement, where you just use the mass of the fuel itself. You try to burn up as much fuel as you can before it blows apart. And then there's gravitational confinement, which is the sun. The sun is a beautiful thing, but the power density in the center of the sun is about like 1 million times lower than what we need for fusion on Earth. So we say that we're building a star on Earth, but we're actually building like an insanely power dense star on Earth. It's really not that analogous. It's very, very different. Okay. Here I'm plotting the cross-section of some of these reactants versus center of mass energy. And we're going to be focusing on DT fusion, so the blue line. And so you'll notice that the cross-section peaks at about 60 keV, 700 million Kelvin. And for those of you who've heard about like some magnetic confinement fusion plasmas, you might say, Jason, hang on a minute, why aren't we aiming for 60 keV plasmas? I always see them around 10 or 20 keV what we're aiming for. And basically the problem is you get a lot of radiation, usually Bremsstrahlung radiation, and transport at these higher temperatures. And it turns out to be energetically more favorable to operate DT plasmas at around 10 to 20 keV. Okay, let's chat about some schemes. So one way to measure the performance of magnetic confinement fusion is this so-called triple product. So you basically, the way to think about it is you've got density N, so you want as much fuel as possible. You want it to be as hot as possible, generally, with caveats. And you tau is the energy confinement time. You want energy you inject in the center of your device to stay there as long as possible. You don't want it to be too leaky. And so here, this is a plot of that triple product versus time. And you can see it looks pretty good from like 1970 until early 2000s, right? Like I would look at that plot and say that's really good progress. And then in the past 20 years or so, we haven't finished building devices that will get into that blue region, which is the triple product we typically need for a feasible DT power plant. Okay. So how might you confine plasma? Well, one idea is that we want many scattering events before a fusion event happens. And that's just dictated by the fact that scattering is so much faster than fusion. So you could take a cylinder and bend it into a torus. Okay. You could heat a gas to a very high temperature. It becomes a plasma. Everything's fully ionized for the fuels that we're looking at. And you could use a magnetic field. You could say, I'm just going to create a toroidal magnetic field. I know how to do that. That's pretty easy. However, so people did this to begin with, like in the 50s and 60s, and they realized if you had a purely toroidal magnetic field, your plasma in a torus is not going to be confined. And the reason for this is that the ions and electrons, they're going to undergo radial particle drifts due to the gradient in the magnetic field and the curvature of the magnetic field. And this leads to basically very fast loss of particles. This is a pain in the neck, and you don't want to do this because it means it's going to ruin your confinement scheme. So what people did is they added a twist to the magnetic field. There are two main ways people add a twist. One is something called a stellarator. So you add the non-toroidal components of the magnetic field using currents outside of the plasma. And we call these non-planar coils. That's basically what a stellarator is. And a tokamak takes a slightly different approach where you actually drive a current through the plasma. Plasma is a great conductor. And so you use that to generate its own current, which is going to generate another magnetic field. Okay, so tokamaks and stellarators have pretty much been the best confinement concepts along with some laser ICF concepts. So this crazy plot, I would just like really focus on like the red dots and these small green ones. These are, this is almost the triple product. This is the density times tau E. You want that to be as big as possible, where tau E is the confinement time. And then this is the temperature here. And this is the promised land, like that we want to get to. We want to get to a point up here where basically the plasma is producing a lot more energy than it takes for us to heat it. You might notice that spark is up here. Spark is hopefully going to be turning on in a year or two. ITER is not going to be turning on for probably another 10 years or so. Also in the past couple of years, NIF at Lawrence Livermore National Laboratory has made amazing progress with how much energy they've been producing. They've been producing a lot more energy than they put in. But I think the engineering of ICF is a lot harder than for tokamaks, even though they have got out more energy than they put in. Okay. This is a lot of text. I don't like slides with too much text, so I'm going to try to not talk too much here. But basically, tokamaks versus stellarators. Why would you do one or the other? So far, tokamaks have better confinement, and they're generally simpler to build in terms of coils. Okay. Disadvantages. You have a multi-mega amp current going through the plasma itself, which can drive lots of instabilities, disruptions. This is awful. Also, they typically require a lot of so-called recirculating power because you have to drive that current. When you get power from a fusion power plant, you convert it into electricity with the steam turbine, and then you have to pay the tax of your recirculating power. You have to pay to power the thing itself, right? And that's a very challenging thing for us to do in lots of tokamaks. Yeah.
I have a question. Do stellarators and tokamaks of the same size perform similarly?
Good question. I think I would say no. W7X does not perform as well as a tokamak of the similar size in terms of triple product. Yeah, it's a good question.
In previous slides, you probably have some stellarators.
Yeah, exactly. Let's have a look.
7X is in W7X is in there.
They should be. There we go. Yeah. So W7X, I think, is about 10 cubic meters of plasma-ish, maybe 20. And I think that's similar to D3D. Or JT6 is a bit bigger. So what's the point? It's interesting, actually. So okay, yeah, here's the problem. Or here's what I think is going on. There doesn't seem to be a density limit in accelerators, right? So you can get to really high density if you can fuel enough, but you can't get to high enough temperature. And there seem to be kind of, people think that kinetic ballooning modes or other types of instabilities in W7X are stopping the temperature from being as high. So yeah, I think long-term accelerators are very, and even short-term maybe, they're very promising, you know. Disruptions don't really happen in accelerators, and that's like one of the showstoppers for tokamaks. Okay, W7X. This is like probably the world's biggest accelerator. Yeah, so there's no current drive in the plasma, right? We use external coils to get the colloidal field. It's more stable at steady state. There's not a Greenwald density limit. Lower recirculating power because you have to drive current in the plasma. That's pretty nice. However, look at that picture. I mean, that's just like, this is a very complicated thing to build, right? Could you imagine manufacturing those in very high quantities? Maybe we will be able to. I think we will be able to, but it's just harder. And okay, I even wrote it here. Yeah, confinement just is not as good for reasons I don't think are fully understood. Okay, so tokamaks, how does this work in a little bit more detail? Well, so tokamaks are so-called axisymmetric, which means if you take a derivative of any equilibrium quantity in the toroidal angle, that's going to be 0 to leading order. It just means you can rotate it round, you know, like in this direction, and it's the same thing. So in order to generate the toroidal field, you need field coils that we generate that run a current in them, which I've just I've noted with J here. And then you have a transformer. This is an important part of the tokamak. So you have a time-varying magnetic field that goes through the transformer and through Curly. You basically get a steady state electric field that is in the toroidal direction. And this is very, very helpful for plasma control and for heating the plasma. This is called ohmic heating. Okay. It also generates a current, which gives you this colloidal field that I'm showing here. And then you can add the toroidal field, which is generated externally, with your colloidal field, and now you get a field line that is no longer purely toroidal. Toroidal is just in that direction. That would be a straight line. But now you can see it's kind of wiggling around a little bit. Okay, that was the innovation that the Russians first did in like the 1960s, and they got very, very good performance, and then the world's fusion programs basically changed to focus on tokamaks pretty much ever since, I would say. Okay. Magnetic field lines trace out these surfaces called flux surfaces. And the idea is that this is very, very good for confining energy and particles. Okay. What are some challenges with tokamaks? I've already told you a little bit, but here's a bit more detail. There are these things called disruptions, where you basically have a sudden loss of plasma. This is not just transport. This is like an explosion of plasma. Current fusion power plants, like here with Alcator CMOD, you can kind of have disruptions and not worry too much about it, although you can see some sparks flying around at the end. But in the future, a power plant can probably only tolerate one disruption. Like the analogy I've heard is like if ITER, which is the world's biggest fusion power plant that's being built, if it disrupts, it probably is going to like break the back of ITER, and like you're going to have to be very careful operating that thing. So just like we can't have even a single disruption. Okay. The tools that you use to prevent disruptions are also have their own drawbacks. So sometimes people use gas puffing to mitigate disruptions. This can generate super fast relativistic electron beams that are carrying mega amps of current. And those things can like drill very fine holes in the side of your tokamak wall. So bad. We don't like disruptions. Power exhaust. This is also another big problem. which is the steady state heat fluxes on the machine wall can be higher than 10 megawatts per square meter. Just to give you some context, the space shuttle had about 9 megawatts per square meter, and that led tragically to a disaster. So we need something that's going to be operating for years or decades with a material that can tolerate those fluxes. So here I've shown heuristically what the fusion power might be in ARC, which might be 500 megawatts. 1/5 of that heat plasma through alpha particles. The other 4/5 will leave as neutrons and will not have to go through the plasma wall because the neutrons just go straight through. So I'm saying 1/5 of the 500 megawatts, about 100 megawatts, is going to be the power through the plasma. Although there'll be other things, you can radiate power. There are lots of things you can do, but there's still a lot of power. Where does this power go? Well, basically, there are these things called diverters, which are kind of where these, you see these bright areas here. And if you imagine these go around the whole device, there's a very small wetted area that is traced out for the diverter. And I've said it's 10 meters. That's a typo. It should be 10 square meters. So imagine 100 megawatts going onto a piece of material that's 10 square meters. It's not much space. Okay, so that's also a big problem. Neutrons. Neutrons are very, very mischievous things, especially neutrons from DT fusion. And here's the reason. So going back to that plot that we had earlier, the average binding energy per nucleon, the absolute highest you can get is about 8.6 MeV for iron, okay? However, a DT fusion neutron in the center of mass frame has 14 MeV. Okay, so its energy is just intrinsically higher than the binding energy of any material that we have. And that tells you something very fundamental about what neutrons are going to do to stuff, right? So yeah, this is very, very hard. Fusion power plants in the structural materials, like the lattice structure can be rearranged tens of times per atom per year. And we've never tested the effect of neutrons in these materials. This is a massive open question that's probably very hard to test until you actually just build a fusion power plant. Okay. Tritium breeding. This is also interesting. So do you remember me saying that tritium is more of a catalyst rather than an input to fusion, at least DT fusion? So what happens is if we go back to this picture, the important point to look at really is this point here. So in the blanket surrounding plasma, neutron is captured by lithium. This is actually technically a fission reaction. It's kind of interesting. Releases energy, gives you helium-4 tritium. This tritium, you have to process through the fuel cycle, and then you whack it back in your plasma again. And the point is that you can imagine there are going to be inefficiencies, there are going to be losses. And so you typically actually need to produce here, more tritium than you're putting into your plasma there. However, you're only getting 1 neutron per fusion reaction. So you have to play games and do fancy things like neutron multiplication and other things in order to make sure that you have enough tritium. There's another thing, which is actually fusion power plants need to build up their tritium supplies over time so they can help other fusion power plants start up, which means they need to make a lot more tritium than they're burning. This is hard. Okay. Last one. There was this very interesting paper that came out about 4 years ago by Mickey Wade, where he performed this cost analysis of what the estimated capital cost of a fusion power plant would be due to reasonable variations in all kinds of different things. So this thing here, the confinement quality, is kind of just like the energy confinement time. Look at how much the cost of this plant is. If you have, say, 1 is the nominal, even a 10% degradation costs you an extra $1 billion. But if you can get to a really high confinement time, 90% higher, then the claim is that your fusion power plant capital cost is much, much lower. And I think the reason is you just don't need as much heating power. The device can be smaller, all those kind of things. Okay, so confinement is actually really, really important. Plasma physics here is seems to be the most important thing for actually determining the price of a fusion power plant, which is interesting because engineers often think, no, it's going to be engineering, but actually it's plasma physics, according to this argument, at least, if you buy this argument. Okay. Here are the challenges. I'm just going to highlight what NSTX-U is looking at. So NSTX-U, which is a device I'll talk to you about for much of the rest of this talk, we're going to be looking at power exhaust and confinement. Okay. Let's go. So first, I'm going to talk a little bit about aspect ratio. So there's an interesting geometric effect that happens in tokamaks, which is the ratio of these two quantities, big R to A. So this is called the major radius to minor radius, and this is the aspect ratio. So spherical tokamaks are low aspect ratio. Okay, they're like really, really, really squeezed together. Conventional tokamaks are high aspect ratio. Cool. Okay, so a little bit more detail. So I'm going to abbreviate spherical tokamaks to STs. That's what people call them. So the aspect ratio is typically 1 to 2. They have something called elongation. So if you notice elongation, it's B divided by 8. You can kind of stretch them in this direction, which means you can like kind of for like a fixed maybe volume, like you can just like pack in a lot more plasma and power density, which is good. Also, beta is a very interesting parameter. For those of you not in fusion, but in other plasma physics, you probably recognize this. In astrophysics, beta of 1 is seen as a small thing, but in tokamaks, beta of like 10% is seen as a very large beta. And it's thought that due to various reasons, you can get pretty high elongation and beta bigger than 0.1 in spherical tokamaks. Conventional tokamaks tend to have less elongated flux surfaces, and they tend to be lower beta. Okay. There are also lots of advantages to conventional tokamaks that I will talk about as well. Okay. So I'm not going to prove this for you now, but some people claim that the total fusion power that you can generate scales as this quantity here. And notice the exponent of 4. And so if you're looking at this, you basically want a device. It's really elongated, has high beta, has high B toroidal. So that's the toroidal magnetic field, and has low aspect ratio. And spherical tokamaks do 3 of those things. You can't get to as high magnetic field with them. I think it's going to come back in a sec. Yeah. But they have high kappa, high beta, and low A. Okay. So getting into this a little bit more. So this is basically a schematic of what the magnetic field lines look like in a conventional device and what they look like in a spherical tokamak. So STs, they're more naturally elongated. And there's this very interesting thing where the magnetic field line spends a lot of time in the inside here. Whereas with conventional tokamaks, they're kind of like half the time they're here on the outboard side, half the time they're here on the inboard side. Why is this important? It's because lots of instabilities called ballooning instabilities in tokamaks are driven by something called bad curvature on the low field side, the outboard side. However, if your magnetic field line doesn't spend too much time in this region, then you might be able to stabilize these plasma instabilities. And that's one very appealing thing for spherical tokamaks. There's this interesting thing called bootstrap current, where basically the plasma generates its own current rather than you needing to use external heating to drive it. And STs can get much higher bootstrap current fraction intrinsically just due to their low aspect ratio. And we think they might have higher power density. Okay, what are some really hard things? Pardon me. Well, one really, really hard thing is that on the inboard side, you're going to get a lot more neutrons hitting the inboard side than you are at higher aspect ratio. And this means that you have to work a lot harder with your neutron shielding on the inside. And this is actually one of the limiting design constraints in STs compared to conventional tokamaks. Yeah.
There are banana orbits. What does the tip of a banana do when it's in that tightly spiral helix down the middle? really the orbit must really look funny.
Yeah, I think those are called like the world's fattest banana. So these are, it's a real thing. It's a trapped particle that just about slows down as it gets to the high field side, right, and then it comes back. Yeah, those things can cause a lot of transport. Yeah, I haven't. Are you thinking about like how that interacts with turbulence, for example?
I just wonder if they hit the wall
Oh, I see.
too fast.
I don't think they're more likely to hit the wall, but I do think they're more likely to spend a lot more time there because of the magnetic field geometry. Yeah. Okay. Some other problems with spherical tokamaks. Basically, I would say spherical tokamaks are intrinsically better physics, but the engineering is way, way harder because you have to build now a solenoid inside this tiny little space here. There's like a lot of important stuff that goes in the middle of a tokamak here. And if you've got a conventional aspect ratio device, you've got so much space, right? But now you've got to squeeze it all inside that little gap. It's very, very hard. And so often the solenoid, which if you remember generates the parallel electric field used for heating, that is often a lot smaller in spherical tokamaks. So in order to start up the plasma, we often have to use different techniques rather than just ramping up with a solenoidal ohmic current. We have to use other ways to start up the plasma. And I'm also just going to say a point that I think is kind of important, which is this thing called scenario development. So it's actually really hard intellectually to figure out how to get to a steady state spherical tokamak scenario because you've got a very high fraction of your current that is so-called non-inductive. It comes from the bootstrap fraction. And to self-consistently do everything is bloody hard. Okay. Next, a little bit more details of interesting things that happen at low aspect ratio. So one is natural elongation. Plasmas because of MHD stability just tend to be more elongated at low aspect ratio. This was a pretty cool thing that Hung in 1987 showed. And so what is going on here? The top plasma is a spherical tokamak plasma, and the bottom one is conventional aspect ratio. And the point is the top one is just more elongated. Okay. Some other cool stuff. So we talked about this a little bit earlier, which is basically conventional tokamak magnetic field lines kind of sample the inboard side and the outboard side kind of equally. But in a spherical tokamak, what happens is they can spend a lot of time on this inboard side. But that means on the outboard side, those field lines, rather than being almost kind of in the toroidal direction, they're actually they're very steep. And this has actually a lot of consequences for something we're going to talk about on the next slide, I think. So yeah, the field spends less time in this bad curvature region as well, which is where instabilities happen. Okay, so I claimed earlier that tokamaks generate the colloidal field with current. That only happens if the current is in the toroidal direction. But now you can see a field line is going in it has a big colloidal component to it as well. So that field line, if current goes along it, is going to generate a toroidal field in and of itself. And this was actually, I think, one of the biggest reasons that people were interested in spherical tokamaks. It's because intrinsically, you can enhance the toroidal field strength that you get in an ST compared to conventional aspect ratio. And it's precisely because those field lines are really steep. So maybe let's stare at the normal aspect ratio one before. That's the major radius, okay? That's the toroidal field. So you can see it falls off as kind of like 1/r, which is like a classic electrodynamics result. Okay, now look at the toroidal field for a spherical tokamak. What's actually going on here is that it actually kind of gets bigger a little bit as you move in major radius, which is a very weird thing. But the claim is that that happens due to those field lines that are very steep. They generate current, and basically you can enhance your toroidal field. So here, Hung found some solutions where the toroidal field was more than doubled in the core of this NST, which is pretty nice. Because toroidal fields are very, very expensive things to generate. Like coils are the most expensive part of a fusion power plant, probably along with cement. So anything you can do to generate those fields internally is better than having to build coils to do it. Okay, there's one last thing that's kind of interesting. If anyone's ever heard of this word called homogeneity, which is basically the condition that particles, when they drift around, they don't move out radially, like they kind of stay on these flux surfaces. And what happens here in the homogeneous region in STs is that contours of constant magnetic field are actually completely in line with the flux surface shape. And this basically means that you don't get any net magnetic drifts perpendicular to the surface. The magnetic drifts just keep particles in the surface. And that means that you're going to get a lot better particle confinement. Usually people think about homogeneity in the context of stellarators, and they do all kinds of optimizations to try to get homogeneous flux surfaces. But in spherical tokamaks, you kind of get it naturally if you go to high enough field. Okay, I'm sorry this thing's flickering, but it's okay. Okay, these are some things that I think are not talked about that much in STs, but I think are very cool. Okay, NSTX-U are the spherical tokamaks. So the claim, which is true, is that NSTX-U at PPPL, it will be the highest power spherical tokamak in the world when it's completed, hopefully soon. So we're adding a second MBI along with a bunch of other upgrades that I'll tell you about in a moment. I'll also tell you what MBI means in a second, because I realize I'm using so many acronyms and not defining all of them. Okay, so yeah, it's getting an upgrade. So what's going on? The toroidal field is being doubled. The plasma current is being doubled. The pulse length is being quintupled, 5 times longer. That's pretty cool. There's a new neutral beam injector. That's what MBI stands for. The heating power, I've written 10 megawatts here, but I think it's actually 12. And because of the angle of that neutral beam into the plasma, the angle of that beam is a lot more in the toroidal direction, so you can drive current a lot more efficiently with it as well. So that's pretty good. Basically, NSTX-U is a relatively small plasma that's going to have the amount of heating that like a big tokamak would have. And so that allows us to study things.
Places where they broke.
Yeah.
So this would be so it's been out of business for a while.
Yeah, since 2016. It broke in 2016. Yeah, they've actually, we're so worried. Well, we were so want to make sure it works that we built 2 solenoids for NSTX-U in case one of them goes. So it will be easy to replace, but I don't think it's gonna break again. Yeah.
So you have this tangential neutral beam injector. What's the point of having the second one that's shooting more perpendicular to the magnetic field?
Yeah, great point. So I think the new one is this one.
Right.
So it's more like following the field lines there. The point is, I think there are a few things. First is, if you imagine that when a neutral particle is injected, it slows down mainly on the electrons, which then go and generate current, okay? So it'll be more efficient at generating current drive in terms of how it transfers momentum in the toroidal direction, which is what we want for current. Second, if you care about plasma rotation, then you might be able to spin up your plasma a lot more with something that's more tangential, because we care about the lowest order, the toroidal rotation of the plasma. Yeah. No, good questions. Okay. It's gone black again. Okay. Here are some more headline things. So the claim is this NT tau thing can be 10 times higher than NSTX. That's pretty cool. The heat flux to the surfaces can be 4 times higher, and like I think higher than any other steady state tokamak. We'll talk about this in a moment. Higher temperature. Oh yeah, this is also really cool. Fully non-inductive current drive. So the goal is to actually be able to operate NSTX-U for several seconds with all of the current drive coming from bootstrap current or non-ohmic current. And that's never happened before in a high beta ST. And for spherical tokamaks, that's what you would need for a power plant.
What would be the trickle factor roughly?
How big? I don't know. Let's go back to our plot and check it out. So NSTX is there. So I'm claiming about here. At least, but then temperature is also going to go up as well. But hold on, I'm showing you N tau, not NT tau. So it's going this way, but it's not supposed to be a machine that's going to ignite or anything. Where's TFTR? That's TFR, isn't it? Or TFTR. Yeah. Well, the thing is, these guys, none of these are really steady state plasmas, and yeah, not even steady state H modes, you know. So I think it's very hard to compare. Yeah, it's a good question.
I think it's the chip value should be larger than, at least should be larger than TFTR.
Yeah.
It's a so old machine.
Well, TFTR was big, it had hot iron mode and a ton of power as well. Yeah. Okay, let's go forward a few slides.
So now in the different how much this.
I think they're aiming for about 70% in some scenarios. Yeah.
What's the rest?
Probably ECCD. Yeah, I think that's the remaining 30%. Is there anything else? That's all I can think of right now. I think it's those two main things. But
For the startup.
yeah, good point. So I think, did I write anything about this here? No, I didn't. Yeah, I'm pretty sure it's going to have to be mainly inductive. We were thinking, I'm going to talk about Pegasus 3 in a minute, which is a device in Wisconsin, Madison. I think we're going to see how that performs and try some of their techniques, but I think it's going to be, yeah. I should ask my colleagues who are working on this though. I don't know what their plans are. No. Okay. A big claim that the spherical tokamak community makes is that the scaling for the confinement time with collisionality is different for spherical tokamaks than normal tokamaks. Why is this important? And what is going on? So first, people plot B tau E. You can show that if you non-dimensionalize tau E to make it dimensionless, you can multiply it by the cyclotron frequency, which in the numerator has a B. Okay, that's where that B comes from. The other factors there seem to be the same. Nu star is the collisionality, and you think that as you get hotter plasmas, you're going to go that way. Okay, so lower nu star. NSTX had a bunch of experiments where they found that the scaling of this thing with that thing was 1 over that thing, 1 over X. Okay. And this was assumed to be very optimistic because people in design studies for conventional aspect ratio think that there's a more pessimistic scaling for confinement time with a nu star than there is for what was found in NSTX. So NSTX-U is going to get to the point where we'll be able to see if there's a bifurcation in the scaling law across aspect ratio. And yeah, I think that's pretty exciting because do you remember how much just like an increase in confinement brought us in terms of the cost of the fusion power plant? So yeah, this needs to be verified experimentally.
So NSTX-U is running, where would the point be?
Yeah, good question. The point would be kind of where these arrows are. The point is, I can't tell you where the y-axis is going to be because that's where the experiment is going to be. If it were optimistic, it would be there. If it were pessimistic, it would be there. Yeah, so nu star normalized is, yeah, pretty small, less than 1 in 100, if everything works out.
And that nu star is collision law as turbulence.
It's just the Coulomb, the electron. Yeah, normalized the electron thermal speed.
Oh.
Yeah, just the vanilla collisionality. Yeah. Okay. I appreciate it's almost 10:02, so I'll try to wrap up quickly. Maybe I'll say some cool things. Lithium. Lithium is an interesting thing because you can put it on the side or the edge of your reactor walls, and you might be able to absorb a lot of the heat. NSTX-U is very interested in doing this and had some cool results at NSTX. This is a cool and important thing. Okay. Some other STs, because I don't want to just talk about NSTX-U, some other STs that are cool. MastU, it has these things. It's called a super exciverter. It means you can spread the heat flux over a much bigger wetted area. Okay. And they've had amazing results. Smart, this is a device that recently just got first plasma, where it's a negative triangularity, low aspect ratio plasma. All that means is the triangles like point in that way. Okay. Most tokamaks have a so-called positive triangularity, where the flux surfaces are flipped. Lots of people are very interested in negative triangularity. This is the first low aspect ratio device to have negative triangularity.
Exactly on that topic, then in that case, particles spend longer time in the path curvature, so what's the argument? Yeah.
Yeah, it's a great question. So this is a
Maybe they find the culture and the culture instability.
exactly in the core, they actually find you get higher critical gradients and lower turbulent diffusivities, which means your gradients can be higher in NT. But at the edge, it's worse. So they can't get into H mode. Okay. So basically, there's an argument: do you operate NT in L mode, or do you operate PT in H mode? That's kind of the debate. The saucy thing that spherical tokamaks seem to be doing is that they say, we think that you can actually operate negative triangularity in H mode in an ST. So you could get much higher confinement. So this is like a pretty new result that Oak Nelson and some others, actually Oak Nelson came here as an undergrad, I think. Yeah, have done on MastU. Yeah, I think this is a very, very big thing for low aspect ratio devices. So yeah.
Will this machine smart be big enough to actually show a good result? Sometimes new machines are built too small.
Yeah, it's a great question. It's at the University of Sevilla in Spain, so it's definitely a university scale device, but they did build it really like with the goal of kind of like being able to nail this question down. So I'm pretty sure they're going to have like serious plasmas in it. It's a pretty, yeah. Yes, they can do scans. The plasma shaping system, they can change it in real time, all kinds of things. Yeah, it's cool. It's a cool machine.
So what's the status of
Smart?
Yeah.
Oh, they commissioned it about half a year ago. They've got first plasmas. I've heard it's running really well. I haven't chatted with the folks recently who work on it, but that's probably because they've just been working very, very long hours getting this thing to run. Yeah. Okay, cool. LTX beta, this is a machine at PPPL where we've actually had liquid metal walls coated with lithium. And there's some very interesting things that happens to this thing called particle recycling and plasma exhaust. Okay, Pegasus 3. This is a really cool device. It's at Madison, Wisconsin. And the aspect ratio is very, very low. Like, can you see here? Like the central solenoid is basically, there's almost no solenoid. It's just the toroidal field course. And so they have to use these things called local helicity injectors to start up the plasma, and they like use magnetic reconnection to start up the plasma. It's very cool. It's very innovative. If we didn't need solenoids to operate, this would make our lives a lot easier for spherical tokamaks. Great machine, great team, exciting stuff. Okay, I'm going to stop talking. This is just basically that lots of people are interested in building fusion power plants with ST configurations. Okay. This is the summary. Basically, this is kind of my joke, but I actually think it's a very important point, which is fusion is cool, but it should also be cheap, right? Like it should be affordable. Spherical tokamaks might be one route to that. Keep an eye out for NSTX-U at PPPL. Hopefully pretty soon it will be up and running, and we're very collaborative. We welcome experimental proposals and other research collaborations. STs have some good things and some bad things. We're trying to figure out if the bad things are really, really bad or not. And STs are a serious candidate for fusion pilot plants. Thank you very much for listening.